This week we'll cover distillation and gas chromatography analysis. Remember, pre-labs are due at the beginning of your lab starting, and the lab report for extraction is due this week as well. Please don't forget to attach all carbon copies of your lab notebook pages and all of the printed spectra. Lab notebook 5 will be checked at the beginning of your lab as well. So distillation sounds, the technique itself sounds a little complicated when you explain it first, but it's a very old technique or ancient technique used for especially fractional distillation used to purify alcoholic beverages after fermentation. They had some residuals from the fermentation cycle, and it's pretty old technique, as I said. Also, if you see the crude oil distillation, they have very cold distillation towers, where the crude oil comes to the distillation tall column and heated over and then separated over their temperature differences. At the bottom, for example, the diesel oil or fuel oil can be collected to be used as fuel in trucks and ships. On the other hand, at the top of the column, low boiling point components collected like gasoline for the cars or gases like propane tanks are filled. The basic theory of distillation includes the purification and separation of liquids. So far, we learned purification of solids by chromatography, recrystallization, and last we used extraction. Again, there are for purification of solids, and distillation is separation and purification of liquids separately. Separating a liquid mixture by distillation based on the boiling point differences. You start heating a mixture of components, liquid components. They shouldn't react with each other. Just mix and then start heating it. When you heat it, it will start boiling and vaporizing the liquid. Then condensing the vapor by using a condenser, and then collecting the condensate or distillate into different reaction receiving vessels. So this is the main technique we're going to use today as well. So the components in a mixture need to have different boiling points for a successful separation. Remember, if you have a pure substance, when you heat that liquid, with the time, the boiling temperature shouldn't change, so it will have a stable line with the time. It's not the case for the mixtures with different boiling points, such as if you have a mixture with similar boiling points. With over time, the vapor pressure will change, the vapor composition change as well. So it will increase, the temperature will increase with time, so the vapor composition changes as well. For example, at longer time, you will collect more higher boiling point component. And at the beginning of the distillation, you're going to collect more or less boiling point component. So the second scenario is the mixture can have very different boiling points. The gap is really high. So what will happen? The first you collect low boiling point component, and there will be a sudden increase in temperature. That shows the heat is used for distilling or vaporizing the high boiling point component. So the high boiling point component will be collected. So again, it's not going to be a constant temperature versus time graph. I have 3 examples in distillation. You can have in case 1, the boiling points are same in the case 1. So what will happen is the vapor composition will be similar, like 50-50% of chance of A and B to be present in the vapor phase. So if you heat it, and then the vapors are going to be condensate, and you will have again the same composition. So there will be no separation in this case. The case 2 is having a little bit difference in boiling points, but they're kind of similar. In our case, it will be less than 50 Celsius degrees, the difference in between the boiling points. You will get more A in the vapor phase. On the other hand, less B in the vapor composition. So when you condensate this distillate, you will receive some separation. And in the case 3 is the best scenario. The difference, the boiling point difference is higher than the other cases. This way you will have more A in the vapor phase and less B, so that will result in a better separation. So this is an example, a very good example for a simple distillation, because simple distillation is most effective when the boiling points of the components differ by more than 50 Celsius degrees, or when the one component is less than 10% in the mixture, you have the best separation this way. The kind of reaction setup shows how to set up a distillation. You first start with filling your round bottom flask with your mixture and a magnetic stir bar or a boiling stones. Then you have the three-way adapter. One way goes to the condenser and the other way attaches the thermometer. So the condenser is connected to the water. Water goes in and out. The outside jacket helps cooling and it doesn't touch to the inside part. Then you have another adapter to keep it. There is an open hole to keep it to the air, open to the air. And sometimes people use receiving flask attached directly, but today we will use, instead of a flask, we will use graduated cylinder. Remember, case 3 was best scenario for simple distillation. But what about case 2? Can we separate very similar boiling point components from a mixture by distillation? The answer is yes, but by using fractional distillation. So in fractional distillation, there is a fractionating column. We're going to use glass beads in our lab this week. The glass beads provides a lot of surface area, and that allows liquid to condense and then re-vaporize repeatedly. So it's ongoing cycle, and in one fractionating column, it's like having maybe 10 or 20 of the simple distillation in one time. The bottom of the column is hotter than the top. There is a temperature gradient, actually. What happens is, at the bottom, there's a high temperature. So at the high temperature, the mixture will condensate back a little bit. But when it goes to the top, it will be lower temperature. And the high boiling point component will condense back. When it comes to the top, you will have only low boiling component at the beginning, and when it comes to the condensation column, it will condensate and only low boiling point component will be collected at the beginning of the distillation. However, when it goes to the middle of the distillation, low boiling point component will be less in concentration, so mainly the temperature will rise rapidly, then only high boiling point component will be collected. So I want to highlight the importance of the thermometer location, and I will highlight why it's so important in the next slides. First, I want to give a little bit background about temperature composition diagrams. So in simple distillation, I will give one example for 75 octane and 25% pentane mixture. This example is from your manual as well, lab manual. So if you start with this mixture, and form a mole fraction of octane on the x-axis and a temperature gradient on the y-axis. The liquid is underneath this curve, the liquid line, and all of the liquids are at these composition and temperatures are liquid, and all of the above of this line is vapor. For example, if you have 20% octane composition at 110 degrees, everything is vapor, for example. And everything is in the middle of this graph is mixture of vapor and liquid. The pure hexane's boiling point is 125.7 Celsius degrees, and 1.0 means it's 100% pure hexane. On the other hand, the left side shows the pure pentane's boiling point, which is 35.1 Celsius degrees. So you start with distillation with 75% octane. When you heat it around 75 Celsius, you get up to the liquid phase. It will start vaporize. And if you stop heating at this position, at this temperature actually, you will hit the vapor phase composition, and then it will condensate, and you will end up around like 18% octane at the beginning of the distillation, and 72% of the pentane. So it's kind of more of low boiling point components achieved. So let's look at it. It says almost 72% pentane achieved at the beginning of the distillation. So if you heat the mixture more, what will happen is it will hit to the vapor phase at the higher temperature, because temperature is gradually increasing. Then if you condensate this mixture at this point, you will end up with 95% octane at the end of the distillation. So you actually obtain two different fractions, which is rich of one of the components at the end. This is the case for simple distillation. Again, the boiling point difference is really high, around 90 Celsius degrees, so it gives a pretty good separation. So let's give another example, which has pentane and hexane. They have very similar or kind of a close boiling points, not like the first example. And if you start from 78% hexane, you can condensate it and get the liquid around 55%. So if you do one more distillation for this, so you can end up with even 27% hexane. Do one more distillation again, you can end up with 10%, and it just goes on and on until you have the pure pentane. So this is the case actually happening during the fractional distillation. So the first fraction gets almost 100% pure pentane, and as the opposite one, at the late part of the distillation, you will heat it more, so around 62 Celsius degrees, you will end up with more pure hexane goes on the right side of the graph. So this is how you can approach and read these kind of graphs. I would like to give a little bit introduction about this. I hope this will help to understand the background of vapor condensation cycle diagrams. Oops. So the task for today, this lab is uses distillation methods to separate a mixture of cyclohexane and toluene mixture. You're going to record the temperature by every 1 milliliter of the distillate, the liquids collected. Then you're going to analyze the two fractions, the fraction A collected at the beginning and fraction B collected at the end of the distillation. Then you're going to analyze them by JC mass spec. I want you to partner with another lab team this week, analyzing the same sample. So one team should perform a simple distillation. On the other hand, the other team should perform a fractional distillation. That way you can share your data and prepare a distillation curve including each distillation data. So you will end up with a graph like this one. It will consist of the simple distillation curve. You expect a constant increase in the temperature with each collected distillate. On the other hand, you would expect a kind of a plateau shape of stable boiling points at the beginning of the distillation and sharp increase in the temperature, and then again another stable temperature in the fractional distillation curve. So this is the best case or most effective separation case for fractional distillation. So I hope you can end up with this kind of graph as well. I want to highlight one thing. Always focus on the y-axis, zoom on the y-axis so you can see the shapes better. If you don't zoom in, the shapes kind of look very similar in the graph. I have some distillation setup tips. This will helpful when you start the distillation setup. Boiling stones will be used, as I said. They will be nucleation sites for the bubbles, so it will not splash and contaminate the distillate. The water jackets, remember, in the condensation column, it should flow opposite direction of the vapors. Please be careful about the water inlet and outlet. The position of the thermometer tip is important. We use alcohol thermometers in the lab, and the dyed alcohol is collected in the bulb section. So the top part of the bulb should be even with the joint, like I lined here. So the top part is exactly at the intersection of the to the joint of the distillation head. The other important thing is the size of the flask. The half of the flask should be full. It shouldn't be more than that. Otherwise, it will again splash to the column and you will not end up with the pure product at the end or distillate. The flask or condenser should be clamped at multiple sides to secure the apparatus and the setup. The metal clamps should be used around the hot parts, especially at the neck is going to be really hot, and I want you to use the actually metal clamps for this purpose. These are the metal clamps, and the keg clips can be used on the other cold parts. If you use the keg clips in the hot part, it will melt and it will cause some fire hazards during the distillation. That's it. I hope you're going to have very high yields during the lab and increase your increase your lab skills in organic lab this week. So hope to see you this week in the lab.